Last lecture we learned how to find prime numbers. Here we learn how to find prime numbers up to number n in big O of log n log n time. It's very fast method, so let's learn it. So the name of the method is Sieve of Eratosthenes. So suppose we have a number 20 and we need to find all the primes up to the number 20. What we do is starting from 2, we know it's a prime number, so we output it. We know it's a first number in the list, we output it simply. Okay, so now what we do is we cancel all the numbers which have 2 as a factor. So we cancel 4, then 6, then 8, then 10, then 12, then 14, then 16, then 18, then 20. Now, then we also remove 2 because we have already traversed it. So now we are at 3. So 3 is also in our output of prime numbers. We now cancel all the factors of 3 that have not yet been cancelled. So we cancel out 15 and we cancel out 9. Now the next number comes 5. We cancel all its factors. So there are all the numbers which have 5 as a factor. So there are no such number remaining. Then comes 7. There also no such number remaining which has 7 as a factor. Then 11, then 13, then 17, then 19. So uh, this is how quick we can find out numbers up to a range, up to a number, prime numbers up to a number n. So here is one question that people generally ask, that suppose I am running the sieve on the first 100 numbers, assuming that marking the numbers are as composite numbers take constant time. The number of times we use mark composite would be something like, for 2 it will be like n by 2, for 3 it will be like n by 3, for 5 it will be like n by 5, for 7 it will be like n by 7, because we need to cancel out all the numbers which have 2, 3, 5, 7 as the factors. So he or she concludes that this is bigger of n square, and to find the next prime number, for example to jump to 7 after crossing out all the numbers that are multiple of 5, the number of operation will be bigger of n. So the time complexity is bigger of n cube. How do you say the time complexity is less? So let's put some things at places. So so we have mark composite that he named as, so the operations we are taking is n by 2 plus n by 3 plus n by 5 up to n by 97, let's suppose, because we are finding prime numbers up to 100 here. So it is not O of n, because the number of, oh sorry, it's not O of n square, because it's a very loose upper bound. A loose upper bound for this is basically 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 up to 1 by n, that is sum of reciprocals of all numbers up to n, which is n log n, because it's harmonic series. And a proper upper bound will be the sum of reciprocals of primes up to n, that is big O of n log n, hence the time complexity. And if we say that the find next prime number is O of n overall, so amortized you will move ahead to find the next prime number only n times in the total, not per step. So this whole part of the algorithm takes only on. So the using these two steps that we marked above, so the upper bound of this algorithm is big O of n log n plus big O of n, that is big O of n log n only. So here's the time complexity. In the next lecture, we'll see how to implement a segmented sieve, and we'll see some questions on it as well. Things a bit more clear, we'll include animation to it which shows how this algorithm is working. The animation is on Wikipedia, so let's open it and see the animation. Here's the animation. So just a sec. So it is finding all the prime numbers up to 121. So first we take 2 and mark all its numbers which has 2 as a factor as false. Same we do for 3, same we do for 5, then 7, then 9, then 11. Oh, sorry, then 7, then 11, and so on till we find all the prime numbers up to 121.